Hi guys, welcome to this quick recording concerning the review for the exam. In this part, which is part 1, I'm going to focus on the problems from chapter 22. I'm going to also record later on chapters 22 and 23 and 24. So right now the focus is on problems. Sorry, okay, I'm struggling with this cold in here. With this, yeah, I think something like that. Runny nose at this point. So I have problem 18 and then 19 from page 745, okay? So hopefully you guys are following with your, I know I gave a handout, so you should have your handouts with you. If not, it should be in the book. This is from the book, straight from the book. I know some of these problems also we did them before, so in class. So hopefully you guys are following also with what he did in class. So it's worth reviewing because again, the exam relies on these ideas. So problem 18, it says that a ray of light strikes a flat 2 centimeter thick block. So I'm gonna draw the block. So the thickness in here is 2 centimeters. And the index of refraction also was given n to be equal to 1.5. At an angle, so it's going to strike it at an angle of 30 degrees. So this is the normal, the angle of incidence is 30 degrees. Obviously, this is the normal extended forever and ever on both sides. And then when it refracts, it's going to refract at an angle usually smaller because the index of refraction in here, I know I should not have written it in here, is higher than 1. So this is the air or vacuum. So for vacuum or air, we know that the index of refraction n is equal to 1. Find A, the angle of refraction at the top of the surface. So they want this angle, which we're going to call it theta prime. Okay, n sine of theta prime is equal to 1 times sine of 30 degrees. That's basically what Snell's second law is. From here, I can find theta prime as being the arc sine of 1 times sine of 30 degrees divided by n. Okay, n being more than 1, so this will ensure that we will get a value that is acceptable. So again, I'm going to plug in the numbers. Arc of sine of 1 times sine of 30 degrees should be 1/2 divided by 1.5, okay, or 1/3. So arc sine of 1/3. 1/6, I'm sorry. No, 1/3. 1.5 times 2, that's 3. So that's basically the answer. So again, I'm gonna pull GeoGebra in here to help me with the calculations. What is the mouse? Oh, I need to remove this from here. I don't know where the mouse is. Never mind. Okay. Come on. Okay. So let me make sure that this is in the proper units in here. Okay, so that's correct. So it's going to be arc, is it ASIN? Yeah, it's an ASIN in this program of 1 sine of 30 degrees divided by 1.5. I'm just writing it as it appears. It's 19.47 degrees. That's the answer, 19.5 degrees basically. Obviously, when you're doing something like this in an exam, you really have to pay attention to your the mode of your calculator, okay? If it's in degrees or radians. So that's why they tested it initially to see what's sine of 30 degrees. So that's the answer to part A. Part B, find the angle of incidence at the bottom of the surface of the refracted. So basically what they want, you want this angle in here with which is going to become incident. This is going to be theta prime. So the answer to that one is theta prime is going to be your theta of incidence for the bottom. Okay, and that's by geometry because you have two parallel lines. Those are the normal to the surfaces, and we just calculated this angle and this angle to be 19.5 degrees, and this angle must be equal to that because we have two parallel lines cut by this one, so they must be the same angle. Okay, so that's basically the answer to part B. Part C, find the lateral displacement D by which the light beam shifts. Okay, and they have it in the drawing. Calculate the speed of light. Okay, so let's do that. Okay, so they want, again, I'm going to redraw the two surfaces just to help me out in here, visualize the problem. So again, we have the normal to both surfaces. We have a ray that came in at 30 degrees. It did not come out at 30 degrees, but rather it came out at 19.5 degrees. Okay, and then as it emerges, it's going to emerge parallel to the initial. So I mean, we can show that this angle is going to be again 30 degrees. Okay, that's because the same relationship that we wrote, namely 1.5 times sine of 19.5 degrees is going to be equal to 1/2, which is sine of 30 degrees emerging from the other end, because the indirect refraction here is also 1. So this two will be parallel, of course. Had it not encountered that object, they want this displacement D. Okay, we can look at it from this geometry in here. Obviously, this is D itself. I mean, this is the thickness of 2 centimeters. So this is, I'm going to call it T. So that is T equal to 2 centimeters. Trying to find a way, so we can find this distance where it's going to land just by looking at the sine of the 19.5 degrees being equal to the opposites over that. And I'm trying to think of a way. Once we find this hypotenuse, basically, of this right angle triangle, this hypotenuse is given by the cosine of 19.5 degrees equal to the thickness T divided by the hypotenuse, which I'm going to call it hip, okay, for hypotenuse, this side, okay, that's what my hip is, the hip. And this geometry in here, we have D divided by the same hypotenuse. This is a normal. Will give me the sine of the difference between 30 and 19.5 degrees. So again, D divided by the same hypotenuse, which we don't know, but we can pull it from this equation here because we have the thickness, we have cosine of 19.5 degrees, and so we should be able to find it. So D divided by the hypotenuse is equal to the sine of the difference between 30 and 19.5 degrees. So all I have to do now, honestly, I really don't need the hypotenuse and I don't need to calculate it. So I'm going to do D over this ratio over that ratio. So that's going to give me D over T, the thickness of the paper, the medium, is equal to the ratio of the sine of the difference between 30 and 19.5. That's 11.5 degrees divided by the sine of 19.5 degrees. Then from here, we're going to pull the thickness being equal to, I mean the separation, how much they shift, the shift. So this is the shift of the ray. So this is the ray shift from the incident to the one that emerges from the other end, from the bottom. So this is given by the thickness times this ratio of these two sines, 11.5 divided by 19.5, sine of 19.5 degrees. Okay, so let's go back to our GeoGebra. Well, obviously you guys need to do these calculations. You're not relying on me to do that for you guys. Okay, so hopefully you guys are going to do that. So let me try to find a different way. Can I call it different than here? Let's call it A. That's for convenience because I can't write much fast. A. So what we have, the thickness D is equal to 2 centimeters. So I'm going to leave it at 2 centimeters. So it's in units of centimeters times the ratio of the sine of the initial angle, the sine of, how much did we say? Is it sine of A? I think the sine of A over, what is the, no, sine of difference. Sine of 30 minus A divided by the sine of A. Okay, you might be wondering, why did I do it this way? And I got a negative number. And why is that? Is it because it's performing algebra in here? I don't like that. Because the sine of 30 degrees minus A, let me do it. 30 minus A first. Okay. You see, it's converting A into radians in here. That's why it's giving me 29.666. So we need to multiply A accordingly. I mean, this is my problem, of course. You're not going to make sure your calculator is in a single mode, okay? So let me convert A into radians, into degrees, because it's, or make this one pi over 6. Yeah, that's faster. Pi over 6. That's what. Okay. So it's 1.1 centimeters. Is that correct? Does it even make sense? So that's how much it's shifting according to this calculation in here. Okay. Of course, you guys are supposed to double check all of this thing, including the reasoning, by the way. Okay. Let me see if I can do it much faster than this. Let's see. So we have 2 sine of 11.5 divided by sine of 19.5. It's 1.19. So somehow the rounding in here is giving me a little bit of a different answer than, because you're dealing with small angles, so small variations of that is really going to affect the answer. So the answer is a little over 1.1, around 1.1 centimeters. Okay. Let me see if I can see what the problem says in here for find the lateral displacement. I have to make sure that my geometry is correct, okay? So this is the hypotenuse. This is where the right angle triangle. So the sine is equal to the opposites of it. Okay, here is the problem. It's not a sine in the denominator. It's a cosine. Hopefully you guys you're screaming probably now from your screen. I'm sorry. I should have listened to you. Okay, so let me fix that. It's a cosine of 30, 19.5 degrees. Sorry about that. I knew something was not 100% correct in here. So this is a cosine 19.5 degrees. Okay, this is where the problem went. It's a cosine, so we do the ratio T over A. So hopefully you guys have caught this mistake. So that's a cosine of 19.5 degrees. So let's go back to GeoGebra and we should find a small value. That's what I was hoping to see, a small value. So this is a cosine of A, not a sine of A. Cosine of A. Cos of A. And let me remove this extra A now. Sorry, I'm dealing with my program in here. Okay, it's not liking it at all. Okay, so that's more like it, okay? So let me write another expression in here involving the cosine. I know you can see it. I better probably delete this too. Okay. So what I'm saying in here is 2. Of course, you're looking at it probably edited. If not, then you're looking at the raw thing. So again, pi over 6 minus A divided by cosine of A. A being extremely small in this case, so it doesn't matter really, honestly, because its cosine is going to be very close from 1. So it's mainly the sine that will give me the answer. So 3.9 millimeters, okay? That's basically what the answer to that question is. So obviously we have to really be picky about the sig figs. So I probably need to make sure that you guys are you know what we're talking about in here. You don't have to, but at least you need 3 sig figs, okay? So the correct answer is 3.88 millimeters, okay? Because that's what the numbers are. They are all of 3 sig figs in the data that was given to the problem. Okay, calculate the speed of light in the glass. Well, the speed of light in the glass, they want it to be calculated. Basically, it's going to be the one that we saw in lecture. So the speed of light in the glass, V in the glass, is going to be V divided by N. So which is 3 times 10 to the power 8 divided by 1.5. So it's going to be 2 times 10 to the power 8 meter per second. Okay? And the answer to that one is 3.88 millimeter. Okay? So they want the speed of the light in the glass, so it's just the speed of light in vacuum divided by the index of refraction, so it's going to be always less than the speed of light in vacuum. So that's known. Then they want to know the time required for light to pass through the glass block. Okay, the path of light, you have to be careful with it in here. You go back to the geometry. It's this hypotenuse. That's the path of light. And it's moving with this speed. So distance over speed should be the time required. So again, the distance is equal to Vt, and from here we can find the time required, which is the distance, which is in this case the hypotenuse, okay? The one that I was talking all along before about, divided by the speed of light in the glass. So this is the hypotenuse because that's really the path that the light took. So in this case, the hypotenuse, I can take any of this expression, is equal to T over divided by cosine of 19.5 degrees. So the time T is equal to the hypotenuse, which is given by the thickness, by the way, divided by cosine of 19.5 degrees, and that divided, of course, by the speed that we just figured it out, which is 2 times 10 to the power 8. It's going to be extremely small time because of the fact that we're dealing with a thickness that is a few millimeters. Cosine of 19.5 is practically 1 divided by 100 million. So it's going to be really 200 million to be more specific. It's going to be really a tiny time. So T is equal to 3.88. No, I'm sorry, it's going to be 2 centimeters. That's what the thickness is. It's going to be 2 centimeters. 2 times 10 to the negative 2 divided by 2 times 10 to the power 8 times cosine of 19.5 degrees. The 2 and the 2 cancel, and I will be left with 10 to the negative 10 seconds divided by cosine of 19.5 degrees. Okay, it's going to be a small time, as I was saying. That's of the order of a nanosecond. That's expected because the distance is extremely low. Even though it's going at an angle with an index of refraction more than 1, it's still going to be a ridiculously small number. So what I need actually is 1 over cosine of A. Okay, so it's of the order of 1 because cosine of A is barely smaller than 1. So again, it's 1.06 times 10 to the negative 10 seconds. Okay, so that's really what we're talking about in here. 1.06 times 10 to the negative 10 seconds, or if you want to really write it in terms of nanoseconds, it's 10th of a nanosecond. Okay, so we found the answer to that part. If the travel time through the block affected by the glass is the travel time affected through the time explained. Okay, it should not be affected because if there was no glass, it would take this path to emerge from the other side. It's a longer path, but it's at a faster speed. And the ratio honestly should be of the order of a 1 over n times n. So at the end it should cancel out. Okay, so the time should be the same. Of course, if you're interested, you should go ahead and calculate it, but the time should be the same. Okay, I need to speed up this process a little bit. So the next problem is problem 19. So problem 19, it says the light beam shown in the figure makes an angle of 20 degrees with respect to the normal n prime, okay, in the linseed oil. Determine the angle theta and theta prime. So let me draw the picture in here so that you guys see it. So we have a water and an oil. So this is water and this is linseed oil. And they gave us the index of refraction of linseed oil, which is NO equals to 1.48. We're going to take the N for water equals to 1.33. So those are the two indices of refractions. And they drew the normal to the separation between the water and the linseed, and they called it NN prime. And this angle in here is given to be an angle of 20 degrees. Okay, obviously this angle also is 20 degrees from the geometry, and the angle in here with which it came must have come from an angle that is more than 20 degrees, because n is equal to 1 in here. Okay, so I have 1 times sine of this angle theta, which they want us to find, and they also want to find the oil when it separates. Okay, the index of refraction is 1.48, so when it bends, it should bend at an angle more than 1.4, more than 20 degrees. So let's find this angle theta prime also. So that's what they want. So the first equation that we need to deal with is to find theta, and for that we have 1 times sine theta is equal to 1.48 times sine of 20 degrees. From here, we should be able to find theta as being the arc sine of 1.48 times sine of 20 degrees. Okay, so let's give it a name and let's calculate it. Okay, let's call it angle D. There is no D in the equations. Okay, D is equal to a sine of, oh, there is a D already in our equation somewhere. E. So let's call it E. It's confusing it with the other E, but that's fine. Let's call it D. D equals to a sine of 1.48 times sine of 20 degrees. Okay, obviously it should be more than, it's 30 degrees basically. 30 degrees, so let's go back into here. So this angle is more than 20 degrees, and according to the answer, it's 30.4 degrees. Okay, the angle theta prime also should be bigger, because the index of refraction is 1.33, whereas the index of refraction here is 1.48. But it should not be bigger than 30.4 degrees. So it's going to be between the 20 degrees and 30.4 degrees. So let's do that. Okay. So what we know also is 1.48 times sine of 20 degrees is equal to 1.33 sine of theta prime. Sine of theta prime is going to be equal to, or theta prime is going to be equal to arc sine of 1.48 times sine of 20 degrees divided by 1.33. Don't take 30.44 and divided by 1.33. That's not the correct answer. Okay, so let's go back into GeoGebra in here to help us with the calculation. So ABCDE equal to, again, a sine of 1.48 times sine of 20 degrees that divided by 1.33. Okay, it's 22.4 degrees. So it's 22.4 degrees, and that's expected. So this angle theta prime is more than this 20 degrees because the index of refraction in here is less than in here, and the difference is not that much. So it's 22.4 degrees, whereas this angle in here is bigger than the 20 degrees because the index of refraction is a lot less than this one. This is 1.48, so it's not 1.18, and that's basically the answer to this problem. Okay, let me see if I can find the next problem in here. Okay, it says in here a narrow beam of ultrasonic. By the way, I'm looking at the same notes that I gave you. Okay, so these are the handouts I gave you last time when we had in class before we were disrupted. So a narrow beam of ultrasonic waves reflects off of the liver tumor in the picture if the speed of the wave is 10% less in the liver than in the surrounding medium. Determine the depth of the tumor. Okay, again, this was, I think we did this problem also in class. So what we have in here, we have the liver and we have a tumor in here. So this is where the problem is. And so light comes in, strikes the liver at an angle of 50 degrees. And light is going to be bent in here because the speed of the sound in this case is 10% less in the liver. So it's going to bend. So this index of refraction is higher if you want to use the law of refraction. So this angle is going to be less. So we need to find this angle basically. Okay. And from here, once we find this angle, they gave us this distance to being from here to here, basically as it reflects, and it's going to come back. As it comes back, this distance they gave us to being 12 centimeters. So this distance from here to here is 6 centimeters. Here is a plan. Once you find this angle, you know the opposite to it. So you can find the adjacent by using the tangent no more. Okay. So this angle in here, again, we're going to use the relative basically speeds. So whatever the speed of sound in this case is v, here is going to be v over n. Okay. And the laws really are going to be in such a way that n, I mean, you can do the time and you can do the argument that we did for light, and it's going to hold the same. So n sine of 50 degrees is equal to, I'm sorry, n sine of 50. 1 times sine of 50 degrees is equal to n times sine of theta prime. So this is theta prime. I'm calling theta prime in this case. So theta prime is going to be equal to sine of 50 divided by, actually the sine of theta prime divided by n. Okay, and from here we're going to find the theta prime, and once we find theta prime, we're going to say the tangent to theta prime is equal to the opposite, which is 6 centimeter, divided by the depth that we're looking for. I'm going to call this distance d. Okay, so once we find d from here, we're going to plug it into this expression. So d is going to be equal to the sine of 6 centimeters, I'm sorry, divided by the tangent of theta prime, and the tangent of theta prime is the arc sine of the sine of 50 degrees divided by n. I mean, it sounds like it's complicated, but it is not. It's just the arc sine of some sine over something. Okay, it's just basically trying to write this symbolically so that I can put it on GeoGebra. So let me go to GeoGebra in here quickly. Obviously you're doing this on your own, and if you have any questions, please do not hesitate to send me a message, because the last thing I want you to is to be confused about these symbols in here. I really should, you guys should not really be confused about what's written in here. And you can go step by step with it. And if you have any questions, please do not hesitate, okay? I really don't want you to be, if this is too complicated, please let me know, okay? Thank you. So again, so we said that it's the 6 centimeter, 6 centimeter divided by the tangent of the arc sine, or the ascent of the sine of how much was it again? 50 divided by the index of refraction in this case, which turned out to be, okay, so it's going to be the inverse of the ratio of the difference over, so it's going to be 1 over 0.9, okay? So 1 over 0.9. I know we went into depth about this one in class. Hopefully you guys okay, so let me explain this thing in here because it's a, so the speed that is 10% in here, okay? So this speed is whatever v is. This speed in here is 10% less. That means it's 0.9 v, okay? So that's what this number is, v over n, which means that it's v over 1 over 0.9. That's how you write 0.9 times v, okay? Which means that it is v over 10 over 9. So the index of refraction n is 10 over 9. And that's why in GeoGebra, sorry, where is GeoGebra in here? In GeoGebra in here, I wrote 1 over 0.9 or 10 over 9, it doesn't matter, it's the same thing, okay? So this is the numerator could be written 10 and the denominator is 9 and the answer is the same, okay? So hopefully you guys see where that 10 over 9 is coming from. It's the fact that the speed is 10% less. That means 0.9 the speed of sound and outside of the liver. So inside of the liver, it acts as 90% the speed of sound outside of the liver. So this can be written as v over 1 over 0.9 or v over 10 over 9. Okay, from here we can deduce the value of the index of refraction that we need to use in the Snell's law, which is 10 over 9. So n is 10 over 9 in here because the speed is less in the liver than outside of the liver, okay? Okay, hopefully this problem is clear, and I know this has applications for your field of expertise, which is biology, okay? I mean, life sciences. Okay, problem 24, it says photons with a wavelength of 589 nanometers in air enters a plate of crown glass with index of refraction n equal to 1.5. Find the speed, B, the wavelength, and C, the energy of a photon in the glass. Okay, so first of all, the speed. So they gave us the glass with n equals to 1.52, okay? And the speed, first of all, is going to be in the glass, similar to the one we did in the beginning, which is the speed of light in vacuum divided by the index of refraction. So in here is going to be some slightly less than 2 or something like that. So 3 divided by 1.52. 1.97, okay? So this is 1.97 times 10 to the power 8 meters per second. So that's the first question. The wavelength is going to be equal to, in this case, lambda naught divided by n. Again, it's going to be equal to, they give us the wavelength, which is 589 nanometers. So leave it in nanometers, don't change it, okay? Divided by 1.52, and in this case, it's going to be equal to what is the GeoGebra? 589 divided by 1.52, and it's 388 nanometers. I mean, it's like a violet or blue or something like that. And the energy of the photons. Okay, there are several ways of finding it. You can find the frequency. The energy should not change, by the way. You can find it in both ways, and it's going to be the same thing. The frequency is equal to the speed of light divided by the wavelength. Okay, and the speed of light is 3 times 10 to the power 8 divided by. Let me first of all write the final expression. So the energy is equal to HF. So it's going to be H times C over lambda. So now I'm going to replace the values. Okay, so the energy is going to be equal to 6.626 times 10 to the negative 34 joules second. Let's put the units in here just to make sure. The energy at the end is going to be in joules, okay? Times the speed of light, which is 3 times 10 to the power 8 meter per second. So this second and this second cancel. Divided by the wavelength, and the wavelength we have is 500. You have to use the original because we are using the original energy. It should not change. If we're going to use a different lambda, we have to change the velocity, okay? So the speed is going to be, so basically I could write the speed in here in the glass being C over N, and the wavelength is C over N, I mean lambda naught over N, okay? And the N cancels, and the expression will be with the original lambda in the vacuum. So whether we write it the energy inside the glass or outside the glass, it's the same energy. So the fact that the light has been refracted does not mean that it has gained or lost energy. So the energy is conserved in here. So that's why I'm writing the expression for the speed of light in vacuum and the wave of this light outside of the glass, okay? Because that's where the vacuum is. Now, if I decide to use the expression inside the glass, then the speed has to be changed by the dividing by n, and so is the wavelength has to be divided by n. And at the end, that cancels. So that's why I'm not really writing the wavelength in the in the vacuum or anything like that. I mean, in the I'm writing them all of them in vacuum, so I don't want, you can't mix. That's my point. You can't put 388 in here. It's going to be wrong. That's the point. If you put 388, you have to put 197 million meters per second. Put this speed then, and it's going to be the same answer. So the meter and the meter cancel. So at the end, as I was saying, this is an energy, so it must be in joules. Okay, -9. So when you're handling problems like this one, always handle the powers first. I have -9 plus 8, so it's going to be 8 minus 9, so that's 17. And I have -34 in here, so it's a -17 at the end. Okay, so the energy is whatever this expression of 6.626 times 3 divided by 589 times 10 to the -17. It's going to be in joules, okay? This number is going to be a small number because I have 589 in the denominator, so I have to be careful in here, okay? So let me go back into GeoGebra in here. So what I have in this case is 6.626 times 3 coming from the speed of light divided by 589. It's 0.337, okay? So this whole thing is 0.0377 times 10 to the -17. This is not in scientific notation, so I have to move the decimal point twice. So it's going to be 3.77 times 10 to the -19 joules. It's worth noting that if I convert it to electron volts, so this is how many joules in an electron volt. So the joule and the joule cancel. So it's going to be, I mean, the 10 to the -19 and 10 to the -19 cancel. So at the end, I will be left with the 3.77 divided by, so let me multiply this by 100. And divide by 1.602. That's the charge of the electron. So it's 2.11 electron volts. So that's another option of saying, okay, either the energy is 3.77 times 10 to the negative 19 joules, which is the same as saying 2.11 electron volt. Both answers are correct. So if you just stick to the electron volt, you're not, to the joules, you're fine, okay? You're not asked to go into electron volt. But it's worth sometimes remembering that in these processes, probably in this level kind of energies, it's probably better to be expressed in terms of electron volts, because it's a number that is 2 is more communicative than, 3.77 times 10 to the negative 19, because 10 to the negative 19 is too small. So there is an order of magnitude in here that is probably, or at least a convenient unit, I should say, for these processes, and that's the electron volt. You don't have to do it for this problem. Down the road, we will see some cases where probably it's much smarter to use the electron volt, especially when doing with chemical processes and chemistry and the binding energy, for example, for atoms and molecules. Then the electron volt will make more sense to use that one, and it's more convenient. But when we go to nuclear processes, actually it's going to be in the mega electron volts, in the millions of electron volts, or sometimes even in the giga electron volts. This is a side note. You don't have to convert for this problem. You can just give me the joules and you're fine, okay? To convert to joules, all you have to the electron volt, all you have to do is to divide by the charge of the electron, basically. Problem 27. Problem 27, it says an opaque cylindrical tank with an open top has a diameter of 3 meters and is completely filled with water. When the afternoon sun reaches an angle of 28 degrees above the horizon, sunlight ceases to illuminate the bottom of the tank. How deep is the tank? Okay, so this is where the problem is. So we have a tank in here, okay, and the sun reaches an angle of above the horizon. So this is the horizon, and this angle of sunlight is 28.28 degrees, okay? So which means that the angle of incidence is this angle, which is subtracted from 90 degrees. Okay, at that point, the light does not show any of the bottom. So basically, it's going to be right at the edge in here. Okay, we know the diameter is 3 meters. So this distance is 3 meters. Okay. And this is the angle of refraction in this case, theta prime. So what we know in here in this case is for water, index of refraction is 1.331 times sine of theta prime. This must be equal to the sine of, because I'm assuming the air is dry enough so that I'm going to use 90 minus 28 is that what, 62 degrees? 62 degrees, okay? So that's basically what this thing is. From here, we can find what sine of theta prime is. It's going to be sine of 62 divided by 1.33. And this is also equal to, in this right angle triangle, is equal to the sine is the opposite divided by the hypotenuse. And this is going to be equal to d divided by the hypotenuse, okay? I really need the hypotenuse in this case, which is equal to the square root of d squared plus the height that I want. This is the height that we want squared, okay, from the right angle triangle. So from here, we can find what the hypotenuse is, and we're going to express it into that expression. So that means d over the square root of d squared plus h squared must be equal to the sine of 62 degrees divided by 1.33 From here, we're going to find d squared plus h squared under the square root is equal to 1.33 times d divided by sine of 62 degrees. All you have to do is just move things around in this case in here in this expression, and hopefully you can see that if I multiply this by 1.33 and divide by that, I'm going to find that. So from here, we're going to find h is equal to this number squared, 1.33 times d divided by sine of 62 degrees squared minus d squared. Okay, obviously under the square root, of course. You square both sides and you subtract d squared, and you take the d squared as a common factor from this expression, so you'll be left with 1.33 divided by sine of 62 degrees and squared minus 1. Obviously, I hope that this is positive number, otherwise we have an imaginary complex number that is not acceptable. Okay, keep all of these things in your head, okay, while you're doing that. So the diameter is 3 meters. That's what this thing is. Sine of square root of open parentheses 1.33 divided by sine of 62 degrees, and the whole thing is squared minus 1. The answer is 3.38 meters. Okay, the answer is 3.38 meters. So that's basically how high this tank is. Okay. One final problem from this chapter. It says that endoscopes are medical instruments used to examine the gastrointestinal tract and other cavities inside the body. The light required for examination is conducted from outside source along a long flexible bundle of optical fibers to the tip, where it exits and eliminates the internal cavity. A lens on the tip collects an image of the light cavity, and another fiber bundle conducts the image back along the endoscope to an eyepiece for viewing. If each fiber in the bundle has a diameter d equals to 10 to the negative 4 meters. Wow, they are very thin. Of course they have to, because they have to go through your mouth all the way to the inside of your body. So their diameter is extremely small, a tenth of a hair basically. Meters. Okay, because the hair is about a millimeter, so this one is a tenth of that size. And refractive index n equals to 1.4. Okay, find the smallest outside radius r permitted for bending the fiber if low light to escape. So basically this is like fiber optics. Here is a problem though. You bend it, okay, as it bends, and they give you the picture also. Obviously I need to do a better drawing. As it bends, so this is the diameter d. As it bends, it's going to be on a radius of curvature. So this is r. So this is how bent it is. The sharper it is, the smaller the r is. And this is the normal, of course, to the separation of the surface. We want the ray, as it hits in here, not to go outside and stays inside the material, inside the fiber. Okay, so that's the geometry that was drawn to you guys in the picture. Okay, so this is the angle of incidence, and this is the angle of reflection. I'm sorry. Okay, see, these two angles must be the same. There is no refraction in here. So in other words, 1 times sine of theta that is going to emerge from the other side must be 90 degrees. This will give me the minimum angle of incidence that makes this one, which is 1.4 times sine of the critical angle. So we need to come at a critical angle in here, theta c, in such a way that the angle of refraction outside the medium is 90 degrees, meaning it doesn't leave, it stays inside. So this is the minimum angle that we need to operate with. Okay, I'm sorry, the maximum angle that we need to go to. Okay, so this is the maximum bending. We can't bend it any further. If we do, then we have a problem. The light will escape and we will have signal that is not clear. The image is not going to be sharp. Okay, so from here we can find what theta c is. Okay, obviously this is 1, so theta c is just the arc sine of 1 over n. Okay, that's basically what we saw in lecture. Now from this geometry you can find what that angle is too. The sine of theta prime is equal to the opposite, which is, this is actually r2. This whole thing is r minus the diameter. So this is r minus d, this distance from here to here, and this is the hypotenuse, which is r. So this is actually equal to the same thing, sine of theta c. Okay, so sine of theta c is on one side is equal to 1 over 1.4, and the other side is equal to r minus d. From here we can solve for r. So basically, let me write it symbolically. So it's 1 over n. So r minus d over r is equal to 1 over n, multiplying both sides by n and r. So it's going to be n times r minus d is equal to r. And from here, we're going to move the negative nd to the other side and move the r to the other side. So we'll be left with r times times n minus 1. So r times n minus this r that moved to the other side, and I took it out, is equal to negative nd. When you move it to the other side, it's going to be nd. From here, we can solve for r. This is the minimum curvature that you can do, that you can do so that it stays, the entire ray stays in. Okay. Okay, so we have in here 1.4 times the diameter, which is 10 to the negative 4, divided by 1.4 minus 1. So from here, r is equal to 1.4 divided by 0.4 times 10 to the negative 4, or 14 over 4 times 10 to the negative 4. And 14 over 4 is 7 divided by 2, so it's 3.5 times 10 to the negative, I'm sorry, what is this negative 14? Negative 4, I'm sorry, negative 4, so negative 4. So it's slightly bigger than the than that radius. In other words, so it's a small angle. 3.5 times 10 to the negative 4 is actually a small curve, but you're dealing with the thin wire in here. So that's why this number is kind of big, and it's about 3.5 times the radius or the diameter of this wire in here. Okay, so again, this is in meters. Okay, so the answer is 0.35 millimeters. Okay, so that's the correct answer for that. Okay, I'll meet you guys for the next recording, for the next few chapters. I probably will need to go slightly faster than this. Thank you.